All right, going over our related rates problems, we have variables that we first need to relate, and then we take the derivative with respect to time so we can relate their rates. That's what our directions say, right? Relate your variables, then relate their rates. So the radius of a sphere is decreasing at a rate of 2 centimeters per second. So radius decreasing, that's a rate, dr dt, is going to equal negative 2 centimeters per second because decreasing implies a negative rate. At the instant when the radius of the sphere is 3 centimeters, so later when r is equal to 3 centimeters, what is the rate of change in square centimeters per second of the surface area? So ds dt is a mystery. We gave you the reminder that the surface area of a sphere with radius r is s equals 4 pi r squared. So there's the relationship between my variables. Now I need to take the derivative with respect to time. The derivative of s with respect to time is notated with ds dt. 4 pi is just a constant. It will just stay in front. The derivative of r squared is 2r with respect to time, so dr dt. Putting this all together, I get ds dt is equal to 8 pi r dr dt. Now that I've taken the derivative, it's later, so I can sub in my 3 for r, and my dr dt I was given was negative 2, so I get 8 times 3 times negative 2 for negative 48 pi. And again, it will be in centimeters, squared centimeters per second, because we're talking about a rate of change of area. Next one, the base of a triangle is increasing at a rate of 3 inches per minute. So the base has a rate of positive 3 inches per minute, while its height, h, is decreasing at a rate of 3 inches per minute. So dh dt is equal to negative 3 inches per minute. Which of the following must be true about the area? Well, the area, increasing, decreasing, right? Those are our options. We need to find dA dt in order to answer those questions. What's happening to the rate of change of the area? So before I can relate their rates, I need to relate the variables. Area equals 1/2 base times height. So now I'm going to relate the rates by taking the derivative with respect to time. This will become dA dt equals 1/2. So 1/2 as a constant in front, and then I'm going to need a product rule between b and h. So first times the derivative of the second plus the second times the derivative of the first, which means that dA dt, the rate of change of the area, is equal to 1/2 b times dH dt plus 1/2 h times dB dt. And now that I've taken the derivative, I can go ahead and sub in the rates that I was given, which was 3 for dB dt and negative 3 for dH dt. So I'm going to have dA dt equals, dH dt was the negative one. This one will be negative, so I get negative 3/2 b plus 1/2 times 3 is positive 3/2 times h. So the question asks then, what is A doing? Is A increasing, decreasing, decreasing sometimes, or decreasing other times? So looking at this, my rate of change of A is dependent on both B and H, which means that we're not always increasing and we're not always decreasing, because we have something that we have a variable that our area depends on. So depending on what B and H are doing, that will dictate when A is increasing versus when A is decreasing. So the next thing to figure out is, let's just do a little trial and error. So when B is less than H, so let's say B was 3 and H was 7, well, you'd end up with negative 9/3 plus 21/3. And so we end up with a situation where dA dt is positive, which means A would be increasing in that instance. You could try it again. Let's say A is decreasing only when B is greater than H. So let's switch that around, make this a 7 and this a 3. So now this one is negative 21 plus 9 ends up with dA dt being negative, which is good because then our function is decreasing at that moment. Okay, so again, we knew it wasn't always increasing or decreasing because dAdt depended on two variables. Last multiple choice. The radius of a circle, dr dt, is decreasing at a constant rate of 0.1 centimeters per second. In terms of the circumference c, well, the circumference of a circle is 2 pi r, the perimeter, the distance around. What is the rate of change of the area, dAdt, is a mystery. We don't have a later moment, but let's think about why we don't have a later. Also, my computer just told us it's 12 o'clock, so great. So let's talk about the area of a circle is equal to pi r squared. There's my relationship between variables. I'm going to take the derivative with respect to time, and I'm going to get dAdt is equal to 2 pi r dr dt. Well, circumference was 2 pi r, which means that dAdt is really just the circumference times the rate of change of the radius. A nice little geometry connection there for you. Well, at this moment, we have our dr dt being negative 0.1. So in terms of the circumference, we're looking at answer choice B. Okay, so this is kind of a typical AP type thing where they ask you, and things seem kind of weird at first, but if you stick to what you know, which is I'm looking for the rate of change of the area of a circle, so I need to find the area of a circle and then find its rate of change, things kind of fall nicely into place with what you can sub in. Okay, last one for related rates. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. So dV dt, rate of change of volume, is 2,000 cubic centimeters per minute. The oil slick takes the form of a right circular cylinder with both its radius and height changing with time. So here's our volume equation that I'll need eventually. And I know that both R and H are changing. Okay, so at the instant when the radius is 100 centimeters, so later when the radius is 100 centimeters and the height is 0.5 centimeters, the radius is increasing at the rate of 2.5 centimeters, so positive 2.5 centimeters per minute. At this instant, so at this later moment, what is the rate of change of the height of the oil slick? So dH dt is a mystery. Okay, well, I've got my variables related, volume, R, and H. Volume, R, and H. So it's actually okay to have all of these variables in here. I'm going to take the derivative with respect to time. So I get dV dt equals, pi is just a constant, so I'm going to let that hang out in front. First times the derivative of the second, plus the second times the derivative of the first. Well, now it's later, so I can sub in all of my information. 2,000 is going to be equal to, pi is just hanging out, 100 squared is 100 times 100, so 10,000. dH dt is what I'm looking for, plus H is 1/2, R is 100, and dr dt is 2.5. I stopped my colors there for some reason, unsure why. So I end up with 2,000 equals 10,000 pi dH dt, plus half of 2 cancels out. 2.5 times 100 is 250. Distribute in your pi. And now I'm working to isolate my dH dt because that's what I wanted to find. So I'm going to subtract 250 pi from 2,000 and divide by 10,000 pi. Now, on an AP free response, leave this. Leave this as it is. Technically, this is in centimeters per minute for units, but you can leave this. If you're like, Ms. Schwartz, I really don't like to leave that. That doesn't look nice to me. Okay, well, you can clean it up a little bit. You could take out a 10 from each one of these things. So you could have 200 minus 25 pi over 1,000 pi. And then I didn't realize too, you could take out a 25. So 200 divided by 25 is 8. 25 divided by 25 is 1. 1,000 divided by 25 ends up being 40. So this ends up being your final answer with a pi still in the bottom. I left that part off. And then this would still be in centimeters per minute. But when you don't have your calculator and it's a free response, you're not trying to make things match. Just leave it, okay? Don't work harder than you need to. All right, extra credit. The rate at which oil is being removed from this oil slick, from the scene, is given by this expression, but we still have oil that's leaking into the slick at 2,000 cubic centimeters per minute. We're looking for the rate of time when the oil slick reaches its maximum volume. So maximum volume is going to be where the rate of change of volume, the derivative, is equal to 0. And then we want to have a change from positive to negative on that volume. So, change of volume. So, justify your answer. The way we can think about this is the rate of change of volume is going to be equal to the 2,000 that keeps getting added into the oil slick minus our ability to remove the oil at a rate of 400 square root of t cubic centimeters per minute. Well, I want to find a maximum, so I'm going to set my derivative equal to 0. Right, because I'm looking for the for the volume having a max, which means V prime has to change from positive to negative. So from here, I'm going to add 400 square root of t equals 2,000. Square root of t then equals 2,000 divided by 400 is going to be 5. T is equal to 25. To justify whether or not this is a max or a min, I could set up a number line talking about V prime. I also, though, could take V double prime. So derivative of 2,000 is 0. This one is going to be negative 400 times 1/2 t to the negative 1/2. And then if I sub things in, negative 200 times 1 over the square root of 25 ends up being a negative number. So the second derivative comes back negative, which means your graph was concave down, indicating that 25 was a maximum. So at time 25, there will be a max volume. So kind of a little relationship with back to testing for maximums, minimums, a little bit of an optimization thing here happening. Lots to think about and just kind of process. But again, the key idea here is that the rate of change of volume would be how much is going in minus how much is being removed. And then we want to think about what does it mean for something, in this case volume, to have a maximum. It means volume's derivative needs to change from positive to negative, indicating a maximum.